Two identical objects start at the same height above level ground, and simultaneously, object A is launched at an angle of 30 degrees above the horizontal, and object B is launched 30 degrees below the horizontal. So just so you can get a feel for what this looks like, I've sketched the two paths. Object A goes along this red path, and object B goes along this blue path. So object A, this is a 30-degree angle with the horizontal. The object goes up and then goes down to the ground. And with object B, this is a 30-degree angle below the horizontal, and it's going down, and it still has a slight downward curve to it because gravity is pulling it as it's going along. So in part A, we're going to draw the free body diagrams. So the only force acting on both objects after the launch is the force of gravity, because air resistance is negligible and there's no more applied force. So it was only an applied force or something acting on it while it was in the process of being launched, but after the launch has happened, gravity is the only force that acts on it. So they should be the same length because the two objects are identical. Part B, does object A or object B hit the ground first, or do they hit the ground at the same time? So when you had the problem before, where one object was dropped and one object was launched horizontally, they had the same initial vertical velocities, the same initial y velocity. But in this case, the two objects do not have the same initial vertical velocity, because the object on the red path has an initial upward velocity, and the object on the blue path has an initial downward velocity. So since they start at the same height, and they're under the same acceleration of gravity, but the fact that one has to go up before it comes down, and the other one just goes straight down, it should be pretty obvious that the two objects are not going to hit the ground at the same time. That the object that hits the ground first is object B, because it's already got the downward motion and it's just getting faster as it's going down, whereas object A, with the upward motion, has to first slow down to zero, to the vertical velocity of 0 at the highest point, and then come back down to its original height, and then go down to the ground. In part C, does object A or object B hit the ground with the greatest speed, or do they hit with the same speed? Well, in this case, we know that they're launched with the same magnitude of the velocity, and they both have the same angle. It's just one's above the horizontal and one's below the horizontal. So the best way to think about this problem is that when the upward launched object, the red path, the ball on the red path, gets back to the same height as where it started. So if I extend this line, this dotted line right here, if I extend the initial height all the way to here, when the object reaches this point right here, it will have the same velocity as when it started. So the velocity here is the same as the velocity here. Just this is the downward or the negative y velocity. This is the upward y velocity, but the magnitude of the velocity is the same. So if the magnitude of the velocity is the same here, and these two have the same magnitude of velocity, just one's going up and one's going down, that means that this, when the object gets to this point right here, it'll have the same magnitude of velocity as object B. So because this object A at this point right here has the same magnitude as object B when it's first launched, they will have the same magnitude of velocity when they hit the ground. They're going to have the same x components and the same y components. In part D, the two objects started at a height of 5 meters above the ground, so we want to calculate how far apart they're going to land. So one way to do this is, if we look at this distance right here, the distance for object B, which we'll call delta x for object B, and we look at this distance right here, that's the delta x for object A. If we calculate both of those distances, Then, to find how far apart they land, which is the distance from here to here, that would just be the distance for object A minus the distance for object B. So that's one way to do it, and we can just use basic kinematics for all of that. The issue in that one, though, is that when you start setting up the kinematics equations, like let's do the path for object A on the upward path. The initial velocity in the y direction was VO sine of theta. It's not 0 because it wasn't dropped. It was launched in an upward direction. So it's going to be VO sine theta. That's the initial velocity was 20 times the sine of 30, which is 10 meters per second. The acceleration of gravity is negative 10 meters per second squared. The delta y, the total distance, the total vertical distance, and this one's a little tricky to figure out. If the object starts here and it ends here, the total vertical distance, the displacement the object's moved, you just look from here to here, and we don't even worry about the path it went on. We just care about where it started and where it ended. And since this has a height of 5 meters, the total displacement is 5 meters. But the other thing is it went downward. It went from here down to here, and we've defined downward as the negative direction. So we've got a negative gravity. So because downward is a negative direction, the delta y would equal to negative 5 meters. And then you could figure out the t, how long it took to get there. And then once you figured out that t, then you would focus on the horizontal direction and just use the constant velocity equation to get the delta x. The issue with this is that if you set up a kinematics equation with these variables, you're going to end up with a quadratic. And even though we discussed quadratics in class, it is really uncommon that you would ever have to actually solve a quadratic. So there is an easier way to do this. So let's ignore all this stuff. And even though it's an easier way to do the problem, it's harder to figure out that way in the first place. But what it boils down to is that we said this velocity right here on the path is going to be exactly the same, but in a different direction as this velocity. They have the same magnitude of velocity. And we know that this angle right here is 30 degrees, which means over on this side, this is going to be an angle of 30 degrees below the horizontal. Now we also remember from object B that it was launched 30 degrees below the horizontal. So these two paths right here and the rest of this path of object A right here, they're moving at the same angle with the same velocity. So basically this whole path for the final part of object A is going to be exactly the same as this whole path for object B. So since we know that this path is exactly the same as this path, if we can calculate the distance between this point and this point, then that would be exactly the same as the distance between this point and this point. So just kind of think of this as like a curved parallelogram. This is exactly the same as this, and this side, which is curved, is exactly the same as this side, which is curved. And it becomes much easier to figure out this distance right here, and then just say when it lands, it has the same distance apart right there. So let's just figure out the distance from here to here, which means we can basically ignore, I'm just going to scribble it all off the diagram, we can ignore everything below that black dotted line and just focus on how far does object A go from the point where it's launched to when it returns to the exact same level. Alright, so the initial velocity, we already established earlier, is 10 meters per second. And the acceleration is negative 10 meters per second squared. Since the object is starting and ending at the same height, right here and right here, we can actually cut this problem in half to make it easier. So when we cut it in half, we can take that top point up there, and we know at that highest point, the velocity in the y direction is equal to 0, And so from this, we can solve for time. So we're going to go through the three-step process after we pick this equation. So the equation we want to use is V is equal to VO plus AT. The three-step process is cancel out anything that's equal to 0. The second step is rearrange the equation for the variable we're looking for. So bring the VO to this side, so it becomes negative, and divide both sides by A. So T equals negative VO over A. And the last step is to plug in the variables. So the initial velocity in the y direction was 10, so we have a negative 10 in the numerator, and the acceleration was negative 10, so negative 10 divided by negative 10 is 1 second. But remember, that's the time it takes to get to this point right here, the halfway point, because we used a final y velocity of 0. So if it takes 1 second to go up, it's going to take 1 second to come back down. So the total time it takes is 2 seconds. And remember, that's the time it takes to get from here, where it was launched, to right here, not down to the ground. From here to here is 2 seconds. So since we know that time, we can now solve for the distance, the horizontal distance. And to do that, we need to get the velocity in the x direction using VO cosine theta. So the velocity in the x direction is 20 times the cosine of 30, which is 17.32 meters per second. And then the horizontal distance, remember in the horizontal direction we can only use the constant velocity formula. So rearranging the constant velocity formula for delta x, we have v times t, so 17.32 times the 2 seconds from right here gives you an answer of 34.64 meters. So since the distance from here over to here is 34.64 meters, the distance from here to here, which is how far apart they land, is also 34.64 meters.